Did you all hear about the cheese factory that exploded in France? There was nothing left but debris. Yeah, that joke's kind of cheesy. I hope you guys are doing okay this morning. The notes that we're going to be using today, the isosceles and equilateral triangles, they are on Google Classroom. If you have a way of printing them or having it on your laptop or iPad where you're annotating over it, you can do that. But they're not too crazy. I think just going off of your own blank piece of paper and writing down important things will work just fine. Pause the video if you need to. I'm going too fast for you to write things down. So first, just starting with isosceles and equilateral triangle, reminding ourselves of what those two triangles are, what they look like. That our isosceles triangle has two sides that are congruent to each other. They do not have to be the left and the right side, and it could be that the side that's not congruent is at any of those sides. But then we've also got equilateral, where all of the sides are congruent. And for the isosceles triangle, we have particular names for the sides and the angles. So the two sides that are congruent to each other, we call legs of the isosceles triangle. So this would be a leg, and that would be a leg. You might think of that as like a table has legs that are congruent to each other. If they're not, your table is going to fall over, or the things that you set on the table are not going to stay on the table. And then the side that is not congruent to the other two is called the base. And a lot of times we do see it oriented like this, where it's sitting on its base, but it doesn't have to be that way. We can draw it anyway. The angle that is in between the two legs is called the vertex angle, which can be a little bit confusing because we call a lot of angles like vertices, but in particular on the isosceles triangle, if they say the vertex angle, then we're talking about the angle in between the two congruent legs. And then the angles on either side of the base are called base angles. For the equilateral triangles, since all of the sides are the same, and we'll find that the angles have to be the same as well, we don't have names for everything, but all of these things we will refer to for sure. Okay. So the biggest theorem that we're going to look at today, this is not one that you need to know by name, but definitely be able to use, is the base angles theorem. Okay, so to look at this, I want you to put your arms on your desk, table, whatever you're writing on, and put your elbows on that surface. So pretend that your arms are the congruent sides of an isosceles triangle. And so your base angles, the base would be whatever surface you're using, and the base angles would be like your elbows, by your elbows. Okay, so look at what happens to those base angles whenever you move your sides out. So if you move your elbows out, your arms are still the same length, and so you still have congruent sides, but notice that those angles are going to stay the same no matter what. There's no way for me to like move my arm. You can't move it in either way, where those angles would not be congruent to each other. If I go in really tight, we notice like now I've got almost 90-degree angles at my elbows, but still they're the same on both sides. And I know you can't see all the way down. I couldn't put the visual where you can see that. If that didn't make any sense, then throw it out. So our base angles theorem tells us, and maybe this was something that we already knew. Which direction? That if I have two sides of my triangle that are congruent to each other, then the angles opposite them are congruent. So if these were my arms here, AB and AC, it's saying that those angles opposite AC and the angle opposite AB, so by my elbows, would have to be congruent to each other. And then we also know that the converse is true. So a little bit of throwback to that word converse, that if this is my conditional statement, if two sides of my triangle are congruent, then the angles opposite them are congruent. The converse would say the opposite is true. And so if two angles of a triangle are congruent, so maybe you've got the situation, this could be your if Let's make them different angles. We'll make this. And maybe you got like DEF. So if you've got two angles of a triangle are congruent to each other, then the sides opposite them are congruent. The angles are congruent. So we would say, if this is true, then I know DF is congruent to FE. So with this theorem, we could use it to draw conclusions. And this first example, it tells us if HG is congruent to HK. So I've got my HG being congruent to HK. Then I would know that my angle, which I've got this small triangle and then the triangle on the right, and then I also have the bigger triangle. So I could be talking about sides of any of them, but HG and HK are sides of the left triangle. So if I have these two sides are congruent to each other, then the angles opposite them are congruent. So I would say then I know angle G is congruent to angle HKG. A little reminder here with our angles that if I have that angle by itself, I knew angle G, there's no other angle I could be referring to. Where for my angle here, I can't call it angle K because that could be talking about HKJ, or it could be talking about HKG, which is what I wanted to talk about. We could also go the other direction and look at two angles in a triangle being congruent. So I've got KHJ being congruent to KJH. And anytime I have angles congruent in a triangle, I've got the opposite sides would be congruent to each other. So I know that my KJ is congruent to KH. So these were separate instances. If they were the same instance, then I would have all three of these congruent to each other if I knew all of that information. So starting to train our brains, just like any new theorem, that now anytime I see two sides of a triangle congruent, I automatically think, okay, I know those opposite angles are congruent. Same thing with knowing that two angles are congruent in a triangle, I know those opposite sides are congruent. And then going off of that, I don't think we've seen this word before, corollary. It's not one that you have to know well, but we see it every now and then. A corollary to the base angles theorem. A corollary just means basically it piggybacks off of it, that it is from the base angles theorem that we can also say a triangle is equilateral if and only if it is equiangular. So if we think about an equilateral triangle, so let's call this ABC. So if I have an equilateral triangle, I basically have the base angles theorem happening 3 times. That if I'm looking at my side AB and AC, they're congruent to each other, so that means that the angles opposite them are congruent, so B would have to be congruent to C. If I look at side BC and AC, the angles opposite them have to be congruent, so I've got angle A would have to be congruent to B. And then we could even do it a 3rd time and look at angle A having to be congruent to angle C, but we end up with all 3 angles being equal to each other based on the base angles theorem, but just using it more than one time. This also means that automatically, I think we brought this up yesterday, automatically whenever I have an equilateral triangle, not only do I know that it's equiangular, but I know what the measures of each of those angles are. Because I know that the sum of the interior is 180 degrees, and there are 3 of them, so each of those angles has to be 60 degrees. So automatically when I see an equilateral triangle, I know it's equiangular and each of those angles equals 60 degrees. So your measure of angle A, measure of angle B, measure of angle C, all equal 60. So then getting into some examples, which again, if you need to pause and draw any of these beforehand, do that. Getting into these examples, I am looking out for congruent sides, congruent angles that would tell me about the other. So in example 1, the first thing that I'm going to do is see, okay, this is an isosceles triangle. I've got 2 sides that are congruent to each other. So I want to go ahead and mark those opposite angles congruent, and that makes answering the question a lot easier because now I know angle y, or just y, is automatically 25 degrees. And now I have two angles in my triangle, so looking for x, I just have x being 180 minus my 25 and 25, so minus 50. So looking out for those congruent pieces. For example 2, again noticing I've got two angles that are congruent this time, so that means that my opposite sides, the sides opposite those angles, have to be congruent to each other. So then remember, anytime we're setting up an equation to solve, this one's a little bit more complicated as far as what equation we're going to write. Don't overthink it. If you ever write that we have two things that are congruent and we're looking for x and we have that expression here, go ahead and set up an equation using that. I know that 4x has to equal 2x plus 4. And these sides have to be congruent to each other. We did not end up using the 10, and that's okay. It's not related to those sides because it does not have to be congruent to them. So then we get 2x equals 4 and x equals 2. And by the way, the directions for all of these was just solve for each variable. So if it did ask you to plug it back in, find dk or dw, plug that back in, and they both end up being 8. Okay, so a little bit more complicated. Example 3 has more than one triangle, but I'm still looking for those congruent sides or congruent angles. So because I have congruent sides here, I know the angles opposite them have to be congruent. In this triangle, I only know one angle, but I do know that v and w have to be the same. So I could set up an equation that says, okay, I've got 40 plus v plus w has to equal 180, but v and w are the same measure, so if I made that one variable, w plus w, then I could go ahead and solve for what that angle measure is for both of them. So I'm going to go ahead and subtract. We got 2 w's, and subtract 40, and we get that w has to be 70. Now some of you are going to go about this the way where you'll subtract 180 minus 40 to begin with and then divide it by 2, and that's all good. The logic behind that is great. Same thing that we did with the equation. Just be careful that if this was more complicated, if you had, you know, v was 2x minus 7 and w was actually a 3x plus 5, that you would know we need to say, well, actually you could set those equal to each other, but know that these are the same. Be able to set up an equation like this where you can solve for those variables. So this was v and w are both 70. Once we have w in particular, it is supplementary to x, so I know that my x plus 70 equals 180. So x is 110. So we're getting there. Ooh, okay, so then it seems like we're a little stuck here. So I've got my 110, I'm looking for y and z. So remember, I still might not be using all the information that I have. Notice that these two are marked congruent to each other. So if those two are marked congruent, that means the angles opposite them are congruent. Now it doesn't mean that y and z have to be the same as v and w. They're their own triangle over here, and in fact it's not going to work because if we had 70 and 70, that's way too many degrees. But y and z are the same, so we can go about it the same way we did v and w, where we've got our 110 plus 2 y's equal 180. Or like I said, we could go about it less setting up an equation and more thinking through each step that I would need to subtract from 180. I have 70 degrees left between the two of them, and so I can divide by 2 to find each one. Okay. With example 4, kind of similar to start with, But instead of starting with an isosceles triangle, we start with an equilateral triangle. Or at least that's the information we know about the sides. So that feels like it may not be enough, but remember, if we have an equilateral triangle, that means the interior was 180, the sum of the interior, so each of these angles have to be 60 degrees. Is equiangular, which allows us to solve for x, so subtracting from 180, our x is 120. And then we have enough information for y. I could either use the big triangle, I've got an angle that's 60, this is 80, and then I'm missing y, or I could use the triangle on the right and say my 120 plus 20 plus y has to be 180, or I could even use my exterior angle theorem and know that 60 has to equal the sum of 20 and y. So lots of ways that we could get there. Probably the most common way is just using that triangle on the right. And we get that y is 40. Which is always good to know a few ways so that I can choose a way and go with it, but then check it with another way so I know, okay, 20 plus 40 does equal 60. It's nice to have another way that we can check ourselves. Okay, last two. I would encourage you here, if you haven't already, pause the video and see if you can try these on your own. Don't just follow me through them, but try some of these on your own. Example 5, we're seeing that we've got congruent sides. So that means the angles opposite them are congruent to each other. This one is a little bit different though. I don't know any of those angle measures. What I do know is that if these are congruent to each other, then if angle D is 2x, angle E has to be 2x. And then I know the sum of all three of them has to be 180. So my 2x plus 2x plus 5x equals 180. So we've got 9x's. X ends up being 20. Alright, and then our last example, example 6, we've got an equilateral triangle, so we know that it is also equiangular. Furthermore, we know that each of those angles is 60 degrees, so if it feels like you don't have enough information, that might be the case for an equilateral triangle. We just automatically know that the angles are all 60 degrees. So my 4x minus 20 equals 60. Definitely, if you thought to make, since all of these are congruent, if you wanted to do 3 times 4x minus 20 equals 180, that works as well. Or your 4x minus 20 plus 4x minus 20 plus 4x minus 20 does equal 180, and that will work the same way. It's just here we've already divided both sides by 3, really, so we found that that one angle is 60. And what do you know? X is 20 again. There's 20 there, and there's 20 there. It's great vision, 20/20. Alright, that is it for today. A lot of these are like a puzzle, so I would encourage you all to not give up on any of the diagrams, but look for those pieces that are congruent, sides that are congruent, angles that are congruent, see what you can figure out or piece together. Look for supplementary angles, vertical angles possibly, and then our 2 new, isosceles equilateral triangles. See what you can get from that. See you guys.